The goal of this lab is to determine the unknown concentrations, the pH and the pOH of 3 different acids by titration. Titration means the determination of the concentration of a solution. The stage which shows the completion of a certain reaction is the endpoint. Equivalence point is a stage in which the amount of reagent added is exactly and stoichiometrically equivalent to the amount of the reacting substance in the titrated solution. The endpoint is detected by some physical change produced by the solution, by itself or more usually by the addition of an auxiliary reagent known as an indicator. An indicator is a chemical reagent used to recognize the attainment or endpoint in a titration. After the reaction between the substance and the standard solution is complete, the indicator should give a clear color change. The neutralization reaction is used to show how an acid and a base combine to form water and a salt. For example, one titration in this lab is HCl plus NaOH, creating NaCl and water. In this lab, an apron was worn to protect clothing, goggles were worn to protect eyes, and gloves were worn to protect hands. For each titration, there were 3 specific acids, 2 different concentrations of HCl and 1 concentration of sulfuric acid, each time mixed with a 0.196 concentration of the base NaOH. Phenolphthalein was used as the indicator to show the titration. The 2 burettes were set up for the acid and the base. The acid was poured into the burette 3 times and drained to get the burette ready for the lab. The burette was filled with acid again to the 0.00 milliliter line, and 12.0 milliliters of the acid were drained into the Erlenmeyer flask. 3 drops of phenolphthalein were put in the acid. The base burette was filled to the 0.00 milliliter line, and some was let out until the liquid turned from clear to a constant pink. The amount varied for each acid. The amounts used for both acids and bases were recorded in the lab books. The contents in the flask were disposed of. The remaining base and acid in the burettes were drained back into their containers and put back away. There were 3 titrations, and each were done 3 times.
All data in the lab was recorded into a data table. Many calculations were used throughout the lab, some of which included average volume used, average number of moles used, average molarity, and so on. The average number of moles used was calculated by multiplying the molarity of the base, which was 0.916, by the average volume of the base, which was expressed in liters. The average number of moles used for the base equaled the average number of moles used for the acids for trials A and B, because all of the mole ratios in the reactions were 1 to 1. However, in trial C, the average moles of acid used was found by dividing the average moles of base used by 2. This occurred because the mole ratio of base to acid was 2 to 1. To find the average molarity, the average number of moles used was divided by the average volume used, which was expressed in liters. To find the hydronium or hydroxide concentration, the constant of water was divided by either the hydronium or hydroxide concentration, which yielded the concentration that was not used in that equation. To find pH or pOH, the negative log of either the hydronium or hydroxide concentration yielded pH or pOH respectively. Discussion.
Looking at the data, compared to other groups, the molarities for acid B and C are different. Personal errors such as not completely drying the flask out after use may have diluted or neutralized acid during the procedures, resulting in a lower molarity. Another personal error included incorrect calculations for molarity. The final personal error included adding too much base after the indicator turned the solution purple. Random errors such as a cracked burette pipe may have resulted in a lost base during neutralization, which would reduce the base volume accuracy. No systematic errors could be reported from the experiment because all of the equipment worked properly.